So good morning, everyone. Welcome back, I guess. Glad to see we're all here. So we talked a bit yesterday about how we controls people, I guess, like to approach physical systems and reason about their capabilities. And I think maybe an interesting thing that came up in the discussion that unfortunately I didn't get time to put together a nice slide about, but I guess is the different concepts of safety and how when I say safety, it kind of often means something slightly different from perhaps the formal verification ideas of safety. And often when controls people talk about safety of a system, we think about the ability of moving the dynamic states in certain directions, etc. So maybe as we're talking, just bear that in mind and try to pay attention how different fields use these same words in slightly different fashions. So we ended yesterday talking about sort of this problem of trying to create simpler multicopters. So how do I create a safe multicopter that will survive the failure of one of its actuators? And one approach is this mechanical redundancy where we add more and more things. And we discussed how it would be nice if you can come up with a simpler design. So instead of having the 4 motors, if I have fewer than 4, I have a cheaper and simpler design. So sorry, just some today, what I want to do is, having yesterday maybe introduced some of the ideas and the approaches, I want to go through a few designs that we did and how we thought about them and hopefully give you some intuition. I'd like very much for you guys to just interrupt me with questions if you have them. I tend to be bad at asking questions, so please just put up your hand or cough loudly or something if you want to add something or if you want to ask something. So I want to give you some examples. And the first example I want to talk about is this question about how do you design vehicles that are capable of flying when they lose some of their actuators. And we saw that the challenge is if I have 4 actuators, it's relatively easy to think about controlling an aerial robot because I can use the 4 actuators to compute 4 independent numbers, 1 being the total force that I want to produce. So this typically should equal the weight for the vehicle to hover, and then 3 being the torque components, X, Y, Z, that allow me to control various points. And once I lose an actuator, I can no longer do this. And then how do we get around this problem? So the way we think about this is we create a model, I guess, as Waleed, there he is, suggested yesterday. And the model we use is this familiar Newton-Euler model that we talked about yesterday as well. So we try to understand how the acceleration, here d double dot, changes as a function of the inputs. In our case, the inputs will be the motor forces, F sub p, how the angular velocity and the orientation changes. And we had this, sorry, let me just move this chair, otherwise I'm going to fall over it. We had this differential equation for the angular velocity, where we had the mass moment of inertia, the angular acceleration, equal to the inputs being the forces that we get to choose, which is included in this tau, the forces we get to choose, the torque of the propellers around the thrust direction, the disturbance torques, and then we had this nonlinear term here, which I said was because of the taking a time derivative in a non-inertial frame. And it is in using these equations that we can then realize how to have one of these things, these vehicles operate in a non-inertial, when you lose one of the propellers. So the key really to understanding how this works is to exploit this cross-coupling term, this nonlinear term in the attitude dynamics. And to derive this is relatively complicated, and since there are relatively few mechanical engineers, I suspect most people have not seen how to get to this kind of equation. So I'm not going to go into it because it's not that exciting, but I want to give you an example of where you will see this in action. So if you take your smartphone, and be careful when you do this, and you throw your smartphone, you can have your phone rotate around an axis, right? So if I do this, the phone is rotating around an axis that's perpendicular to the screen. And we notice if I look at the rotation, as you would expect, once the phone is in the air, there are no torques acting on the phone and the rotation is relatively boring, right? So it just keeps rotating in this direction. I can do the same, rotating it around the thin axis, and we see the same thing happens, right? So I have the phone rotating around the direction like this, and as it is flying through the air, that doesn't change. If I throw the phone to rotate around this axis here, though, something kind of surprising happens. So if we just look at what happens, we note that initially the phone is rotating nicely, but then something complicated happens, right? And And that is exactly this term that we see here. So even though there are no torques acting on the phone when it is rotating, there is an angular acceleration, right? And that's different in rotation than it is in translation, right? So Newton tells us if there are no forces, there is no acceleration. In rotation, that's not true. And it's not true because of the complexity of the mass moment of inertia matrix, loosely speaking. But we can use this idea now to try and control an aerial vehicle when we lose an actuator. So we can use this sort of nonlinearity to try and control the vehicle. And what we did yesterday is we talked about how do I create a vehicle to, say, to survive disturbances when doing inspection. And we saw that the way to analyze this was to try and linearize the system around its equilibrium conditions. So we try to describe where we want the system to be, and then we talk about small perturbations from this equilibrium. So small differences from this desired position, and then we can analyze what happens to these small disturbances. So in this case, it is slightly more complicated to talk about what an equilibrium is. So we argue that you can have the vehicle remain stationary, hover, but we have to sort of redefine what we mean by hovering. So if I have 4 propellers, hovering is simple. So you can have an aerial robot that just stands still in the air with the thrust vector pointing upwards. If I lose one of my actuators, this is no longer possible. And what I can do is I can define this relaxed hover, we call it, where the idea is to have a condition where the system will have, on average, 0 acceleration. So rather than really being stationary, it is on average stationary. But of course, what that means is that over some long time, it stays roughly at the same position. And we also sort of put this requirement that from the perspective of the vehicle, everything remains constant, right? So you can imagine that if you glued a camera to the quadcopter and you looked at, say, the angular velocity, this does not change over time. You can express this mathematically using the differential equation by setting the derivatives to 0, and you get sort of some algebraic equations that look something like this. So this is basically just encoding that the average acceleration, that is the acceleration over some period t, has to be 0. And this bottom equation encodes this idea that the angular acceleration must be 0. You can then solve this and you find sort of this nice mechanical solution, which is that the vehicle has to be rotating around the vertical axis, right? So it's either going to be stationary, or if it's not stationary, it has to be rotating around gravity. And you have these periodic solutions, and I'll show you a video to show you exactly what these periodic solutions look like. But what's kind of interesting is you can now take your aerial robot that weighs perhaps half a kilogram, so 5 newtons, and if you have 4 propellers, you would have an equilibrium where each of the propellers produces an equal force, equal to a quarter of the vehicle's weight, and of course the vehicle is not rotating. Now, if I have a failure acting on my system, so I lose one of the actuators, we can compute this equilibrium state, this relaxed hover solution, where the vehicle is going to rotate at something like 20 radians per second, which is about 3 hertz, so 3 rotations per second. And we notice that, of course, the motor forces go up slightly. So to have the vehicle fly, you need to produce more forces, which is what you would expect. You can also compute a solution when you have 2 actuators failed. So if I remove 2 of the motors, where each propeller now has to produce half the weight, and the vehicle is now rotating at about 30 radians per second or 5 hertz, so relatively fast rotation. Now, of course, you note that these are 2 particular motors that have failed. If you choose 2 adjacent motors, you can also find a solution, but it's much more difficult to actually have it fly. So these are sort of 3 interesting cases that we can design a vehicle or have a vehicle run and experiment with as well. So what this suggests is that I can find a condition for the system that if the system is in that condition, it will stay there, right? So if I have a multicopter with a failed motor and I can bring it to this angular velocity with these forces, it will be able to maintain an average position in space. Now, of course, that's only half the problem, right? So we understand that not only do I need to be able to hold my equilibrium condition, but I need to reach that equilibrium condition, right? So initially I might be at some undesirable state, so there might be some disturbance acting on me, and I need to move the system from that initial condition to this final condition. And that's what we talked about yesterday when we were thinking about these disturbances. How do I choose the inputs to respond to these disturbances? Sort of the same kind of question. Here it's kind of interesting because it's not intuitive how this works, right? So when we had this 2-dimensional quadcopter yesterday, it was very easy to understand that if I create a torque that rotates the thrust direction, which allows me to push the vehicle around. For this 2-propeller quadcopter, it's clear that if I want to rotate around this axis, I can use a differential force, right? So if this propeller produces more force than this, the vehicle will rotate in that direction. But there's no input to cause the system to rotate around this axis here, right? Which is kind of the harder part of this. Luckily, though, we can use this nonlinearity, and it's actually pretty easy to do once you've written down the equations to actuate this. So we'll use the fact that when you have a body rotating, because angular dynamics couple through the matrix of the mass moment of inertia, you can create two components of angular velocity and have this cause an acceleration in a third direction. And then much like we did yesterday, you can take the nonlinear equations and you can linearize them. So yesterday we looked at the horizontal subsystems. Here we're looking at sort of the attitude subsystem. So we have, again, a four-dimensional system. The states here are two components of angular velocity and then two components of direction. So we will have a four-dimensional system. We have a linearized system, so you can express everything in matrices. And the takeaway here is that once I have this nonlinear equation, these nonlinear dynamics, and I understand what the equilibrium is, making this equation is trivial. So this you can also do using symbolic tools on your computer. And once I have this, I can analyze the system. So I can reason about how well can I respond to disturbances, and I can also use this to reason about different designs. So if you look at this matrix equation, we note that the matrices are relatively sparse, so lots of zeros and ones, and then there are these sort of two interesting numbers, A and R. So R is the speed with which we're rotating. So this vehicle is rotating around its thrust direction. I'll show you a video in a second, and then you'll have a clear mind's picture of what that means. Not that interesting. What is interesting, though, is this A bar. So this A bar is some mix of the mass moment of inertia entries, so basically where the mass is in this physical system. And by changing where I put the mass, I can change how controllable the system is. And it turns out if you build a quadcopter that's very flat, so where all the mass is sort of concentrated in a plane, you cannot control it using only two propellers. If you build a quadcopter which is sort of spherical, so where the mass is roughly equally distributed around the center of mass, you can also not control it in this fashion. So this gives us an intuition that if I want to build a system that I can control in this sense, so a system that is actually capable of operating when I lose some of the propellers, I need to put the mass in a certain configuration. So I need a system that's somewhere between a pancake and a ball to control it. But once I have the system that I'm happy with and I have this configuration, it's relatively easy for us to design a controller. And I guess Waleed yesterday showed us to design a controller for the one car to follow the other. And it's basically the same idea. And I'm not sure if you're going to design more controllers today.
I don't know. We'll see.
We'll see. I hope so. Because I'm not going to talk too much about it. But then I designed these controllers. And again, in this case, because it's a linear system, there are very easy tools to design these controllers. So don't let the differential equation square you. And then you can create a system like this. So this is now going to be a quadcopter that's going to take off. And for some reason, there's no sound still. OK. Well, so we're looking at a quadcopter taking off. This is a view of that propeller. And there's a nut that's supposed to hold this propeller down. The nut is missing. So the propeller eventually vibrates loose. And of course, what happens then is it's no longer possible for this vehicle to fly. So let's just play that again because I kind of got distracted. So there's supposed to be a nut here which holds the propeller down, but this nut is missing. So it's just held on by friction. And as it is flying, this friction is not quite sufficient to hold the propeller down. So eventually, it will fall off. So we see this failure happening. Of course, initially, the vehicle is then suddenly missing one of these forces. So it sort of starts to tilt over. But then we can use this alternative control mode to fly the quadcopter back. So it's able to recover to its original position. And we can look at this again in slow motion. So this is the propeller that's going to fail. So we note initially the vehicle tilts over. But then it's able to use this alternative control strategy to recover to its original position. And this means that you suddenly have a safer multicopter, right? Because you have a quadcopter, which we would have said is not safe because I need all four propellers to fly. And it's true, I need all four propellers to fly normally. But if I'm allowed to cheat and use this sort of relaxed definition of hovering, I can still fly if I lose one of my propellers. Of course, this will not be useful if you're trying to, say, take photographs of people's houses and you lose one of your propellers. Your photos are going to be mighty blurry. But at least in sort of the safety sense, you can now bring this vehicle back home safely, right? And you have the ability to bleed off the potential energy that you had when you were hovering high and bring the vehicle to soft landing, even if you can't control the orientation, the yaw angle. We can use the same idea sort of to create new types of vehicles. I just quickly want to talk about two interesting examples before bringing it back to the safety of quadcopters. So we talked about sort of quadcopters, and then we saw if I fail a propeller, I can still fly. So you can use this idea then to say, well, how many propellers do I really need? So we built sort of this family of vehicles. I want to talk about two of them. The two-propeller vehicle here, and then a one-propeller vehicle, which we claim is the simplest vehicle that you can create. So the two-propeller vehicle was a quadcopter where we literally just sawed two of the arms off. And naively then, okay, it's the same as the quadcopter with two propellers, and you should be able to fly. And of course, eventually, we were able to fly. But it was very difficult to get the system to operate. And I just want to show you some of our difficulties with this. Okay, so what do we notice here? We notice that there's this extremely rapid transition from controlled flight to this flip over failure where the vehicle then crashes. And this was instructive for us being sort of naively just trying things and hacking around, because it showed that even though this vehicle is theoretically capable of flying, it was very sensitive to disturbances, right? So if you did the analysis, this is a controllable system, and it should work, and it does work, but the ability to reject noise inputs, to reject these disturbances, was extremely poor. And why this happens is if you look at this vehicle, we're rotating around this z-axis, so this vertical axis. And if you compute the mass moment of inertia, you can sort of look at this skinny axis here. So this is if you look at your phone, that will be the thin axis of your phone. Then we had the fattest axis would be y, that's this axis here. And then we were rotating around the middle axis. And the problem with rotating around the central axis here, and this is what I showed you with the phone, is that this is not stable. So again, let's take the phone, you throw it around the thick axis, you get a really clean rotation. You throw it around the thin axis, really clean rotation. You throw it around the middle axis, and there is no way that you can get it to rotate if you throw it with any reasonable amount of speed without having this weird rotation happening. And that's exactly what we did with this vehicle. And the point here is that if you're not careful about your design, you can end up with something that is very poor and very difficult to control. And this is something that happens often when you design fighter aircraft. You design them on purpose to be unstable, so to have this property, which means that they can react very quickly. But it also means that if your automatic controller does something bad, the system will fail much quicker than you can respond. Right? So you have this instability that you cannot catch as a human, and that just sort of raises the danger level of your system quite a lot. You can also use this idea to build this vehicle. I just quickly want to point it out because I think it's kind of interesting that you can create fundamentally a brick with a single propeller attached to it, and you can have this object flying. We claim this is the simplest mechanical flight-capable system in existence. What does it look like when it flies? So this is what the vehicle does when it's flying. So we notice it's rotating. So you have your single thrust direction. In slow motion, we notice the thrust sort of points to the side, and then as the vehicle rotates, this averages out so that the vehicle remains on average at the same position. So not only can you hover, you can also sort of fly around. So to get the vehicle in the air, you throw it like a frisbee. And then we can use this magic wand that you'll see come up in our Duke Nukem view in a second. And you can point to points in the wall, and the vehicle will then track these points. Right? So you can create these extremely simple flight-capable machines. Clearly, for taking photographs of real estate, not so useful. But if all you need to do is get an air quality sample, you can imagine that this might be a really cheap way to do something like that. And again, here you can ask yourself, how do I make this system easy to control? How do I make this system reliable, able to reject disturbances, etc.? And for this system, it really depends on the mass distribution. So as with the quadcopter, where does the mass reside? And where does the propeller sit on this design? So what we can do is we can use fundamentally the same math tools that I talked about yesterday, where we can compute the sensitivity of the system to the disturbance, in this case, say, noise on the sensors. as a function of where we place the electronics. So the idea in this picture, and it's relatively complicated, so let me just walk you through it, is in the system there are three sort of massive components. The massive components would be the motor, the battery, and then the electronics that compute everything else. And initially we just had these three massive components on an equilateral triangle. And then we asked ourselves, if I move the position of the electronics around, keeping the other two fixed, how does the robustness of the system change? So how does the sensitivity to external disturbances change? And then what you get is you get this plot here, which shows you, loosely speaking, how likely it is that the controller will fail as a function of the disturbances. So if you're in the blue zone, it's extremely likely, it's almost certain that you will fail. And if you're in this sort of cream-colored zone, it is extremely unlikely that this design will fail. And what we see is that there's a sort of very clear dependency on where you put your mass, so how you design this vehicle, how you build it to make it easy to operate. So if we had designed the electronics to be in the blue region, it would be extremely difficult to fly this vehicle, and it would probably have looked a lot like this stick-like vehicle that I showed you earlier. But instead, by sort of reasoning about the robustness as we're designing the system, you get a very easy to control system. And that's often the secret in robotics, is we cheat. So we make the problem look really difficult, but we make it really easy. So if you're a good controls engineer, at least in my opinion, your controller is always really, really simple, right? Because you've done the hard work in the design stage, right? So you make the system easy to control, so you don't need to do any difficult control work to actually design the controller. So this is nice in the lab, right? So you can create cool videos, but who needs it? What's it good for? So this is something that actually we have patented that the company is using for sort of safety critical systems. So the idea is, if I take the stick-like vehicle, I know I can fly it with two propellers. So if I take two of these and I glue them together, I get what is a quadcopter, but really consisting of two independent, totally controllable and flight-capable vehicles. Now, if I glue them together, I get the mass distribution of my original quadcopter, which was much easier to work with than the stick-like vehicle. But I effectively have totally independent systems. So each of these will have its own sensors, will have its own power system, will have its own independent communications, which gives me full redundancy, right? So any individual component can fail, and my vehicle will have a body that's capable of carrying it home if something like this happens. This idea is then used by this company, Verity Studios, for example, to create theater performances where you have drones that are part of the show. So these drones act effectively as high-tech props, right? So sort of like the people that fly around on wires, you can have drones flying around as well. And this was used in the show Paramour, which was made by Cirque du Soleil, which unfortunately is no longer running. And there's no sound, so I'll just have to play the video quietly. But it's a typical Cirque du Soleil musical, so you have lots of singing, dancing, very spectacular, lots of stage automation in the background, so everything is sort of moving around. And then as part of this, Cirque du Soleil wanted the ability to have sort of these three-dimensional props that can move around in an unconstrained fashion. So they wanted to have drones that can operate. But of course, you need these drones to be safe. And there are two things to worry about. One is obviously you don't want to injure any of the actors, so you don't want the drones to fall on the actors. And the other thing is that the whole point of going to the theater is you want to be close to the stage, right? It's this very intimate experience. So you don't want to put a physical barrier between the performers and the audience. So you don't want a net, for example. So you need a drone system which is sufficiently safe to allow you to do this. And then this company was able to convince Cirque du Soleil and the insurers, etc., that using this redundant technology gives you a system that you can use in this very high-pressure environment. So this is just a clip showing you what the drones do in the show. Unfortunately, it's not a great clip. The reason for this is that Cirque du Soleil has extremely annoying copyright rules, so I can't show you sort of my own footage, but I can show you the stuff that they released. So you'll see here sort of the drones flying around. The story is a love triangle, so the lady falls in love with two people, and then at the first kiss, sort of everything magic happens, the world comes alive, and you have these drones start to fly around, and it gives you sort of a very interesting effect that is at the time at least, was sort of a unique selling point of this particular show, right? So no one else had the ability to do this. And really here, the key that enabled this was the safety technology. And just to give you an idea, this show had 8 drones that had 8 shows per week in a theater with a capacity of 2,000 people with tickets on the order of $100. So you can imagine if you have a failure that stops the show, that is hugely expensive. So not only do you care, of course, about not hurting people, but the economic cost of a failure is extremely high. So it's not, I need to now send a person in a helicopter to take my photographs. Here you have 2,000 people that you need to refund $100 each, right? So it's an extremely expensive endeavor. And just maybe a quick comment here. This ran for about a year, I think. I think in this time, this technology that I was just describing was never actually used. So no failure ever occurred that required this to be used. But I guess the point is that that's kind of the ideal case for any safety technology, right? Is you have it there, it gives you confidence, but ideally you never need it. Ideally you never need to deploy your parachute. There were some other safety failures that happened, but these just grounded the system. So, for example, an artist would have stepped on a drone before it was supposed to take off, and then the operator just said, OK, I don't know what just happened, but I'm not going to allow you to fly today. And then the audience just gets a slightly reduced performance. I want to quickly talk about 2 other designs that we've been doing in our group. One of them is very closely related to the example that we talked about yesterday. And then there's one which is not so much related to safety, but it's just sort of an interesting mechanical design that I want to talk about. Before I get to that, Martin will tell us that you can only pay attention for 30 minutes without a break. So I want to ask, are there any questions or any comments before we move on? Yes, Lars. No, so this was the operator had to push the start button and that's it. So the issue is when you have this many, specifically 8 drones, it's very hard for any person to keep track of what's going on. And I think it would be very difficult to convince anyone that you have a system where you have 8 people that pay sufficient attention in this complicated environment, at least for a reasonable cost. So here everything was fully autonomous up to the start and the abort button. And just sort of as a comment, the abort procedure was not only, you had some monitor that told you if, say, the battery, something was going on, etc. But there was also someone that basically was looking at the edge of the stage. And if they noticed the drone crossing a certain line, they had a big button that they would hit that would cause the drones to just sort of fly back to the back of the stage. But that was the only thing that the people did.
How did you do localization in the...
I think that's secret, unfortunately, so I can't really talk about that.
So, given that there's obviously some indoor system, if you're outdoors, could you just use GPS, or would you need an extra sort of...
So we've used GPS for this failsafe as well, and it's fine, it works. In principle, it's not harder to fly than a normal quadcopter. The trick is that you need to, in software, just do a little bit of work to translate what the normal forward and back commands would be in this rotating frame. But if you imagine having a compass on your system, you can use the compass to pretty easily give you the direction that should be forward. Even if compasses tend to be very noisy because you get this nice sine wave. So you can very quickly effectively get the phase of the sine wave to tell you which direction is north. So there's some cute tricks that you can play in that front.
Yeah. And how about your 1- and 2-bladed things within wind or... Because you talked yesterday about...
So yeah, you get some advantages, and actually I'll talk about some of the advantages here when you have rotating components and how this helps you be more stable. I'm not sure how, with wind it's always hard because it's hard to predict exactly what the forces are, because as you're rotating, because typically drag forces are quadratic in the speed, it's hard to say if you might just have much larger forces given a wind gust because I'm rotating compared to not rotating. So it's kind of hard for me to predict.
Have you tried insuring anything outdoors yet?
I have not. I don't think so. I used to be with this company, Various Studios. I'm not sure if they have. But when I was there, everything was indoors. Because in part, when you're indoors, the Federal Aviation Administration or the European one have no say, right? So the moment you're flying in the outdoors, you're immediately subject to all of the aerospace regulations, which can be extremely onerous. But the moment you're indoors, you just need the building owners to sign off. And they are easier to reason with, potentially.
So you simplified the problem.
Exactly. We cheated and made it easy for us. So what I want to talk about now is this design here, where we're interested in how do I create a system that's capable of surviving sort of extreme disturbances. So think about large wind or extreme weather. For example, here, we have these terrible hailstorms, you have big wind, you can have other things happening as well. So how do I create aerial systems that I'm confident can reliably operate in these sort of conditions? And again, we start with sort of our dynamics, right? So we can analyze how the disturbances act on the translation and on the rotation of these systems. And we've seen this before. And the question was, how do I change these dynamics to make it better for the system? So yesterday we had this example about changing the size, and we saw that bigger vehicles will be better. But of course, bigger has its own problems. So if I have something that's more massive, it will be much more energy intensive, so I will need bigger batteries. It will be more dangerous in the sense that it's just got more energy to deal with, etc. So what else can I do? And the intuition we were exploiting for this particular design is sort of looking at how spacecraft keep their orientation. So when you're thinking about, sorry, just to go back quickly, these vehicles, the ability to hold a position in space is effectively the ability to keep your thrust direction, this direction Z, pointed where you want it to be pointing. So if you think about torque disturbances, which will be for these kinds of vehicles probably the dominant disturbances, the question is, how do I design a vehicle where this direction, this thrust direction, is pointing in the same direction as easily as possible? So one idea was to make the vehicle just much more massive. An alternative idea is to use the same technologies as we use in spacecraft to point the antenna disk. So if you have a spacecraft, and this is Galileo going around Jupiter, you need to point your antenna dish very accurately at Earth to be able to transmit the data at the distance. So the way we do this is we have this dual spin concept. So we have one part of the spacecraft rotating at relatively high speed around the direction that we want to keep stable. And much like spinning a top on a table or trying to balance a basketball on your finger, having this rotation makes the problem much easier, right? So anyone that's tried to balance a basketball without rotating it will know that this is basically impossible. So we use the same idea with these vehicles. And again, we do it in this very model-based fashion, right? So we try to reason about what would be the effect if I take my normal quadcopter and I now add this rotating mass, the second dual spin component. And I have this dual spin component rotating with some angular velocity, here omega WB, that's the speed of the wheel with respect to the body. What would be the effect of this wheel on the dynamics of the system? So my design parameters would be how I design the wheel, so what is the mass distribution of the wheel, and then how quickly do I rotate the wheel with respect to the body, so the angular velocity of the wheel. And again, we would compute an equilibrium, and then we can analyze the effects of disturbances on this equilibrium. Our inputs would be the same for motor forces, or alternatively, the 3 torques and the total force, and we can now reason about the system. So again, you would end up with some linear system that looks something like this. And initially, I guess if you're not used to this, you think, oh, wow, this is really complicated. But once you've seen a few of these, this is actually a really simple linear system because, again, it is extremely sparse, so lots of zeros. And the numbers that are in these matrices are relatively simple, right? So you have 1, you have the magnitude of gravity, and then you have this one magic constant here, which depends on the mass distribution of the body, the wheel, and the speed of the wheel. And then your inputs, so here we're looking at the horizontal motion in the 2 horizontal directions. So our inputs would be the 2 components of torque perpendicular to the thrust. And the inputs are sort of conditioned through the matrix by the mass moment of inertia. And what happens when I have this dual spin component compared to the example yesterday is that I can no longer decouple the motion in the 2 horizontal directions. So in yesterday's example, when we talked about the multicopter, we could reason about the x direction in the world and the y direction in the world separately. And what happens now, because of this rotation, is the x and y components will be coupled through this blue term here. And this is very much, if you think about spinning a top, for example, bumping the top in one direction, what you'll see is that it starts to wobble, right? And this wobble has components in both horizontal directions, right? Not just the direction that you've bumped it in. And you can compare that to the case where you don't spin the top. So if you just balance the top and you bumped it, then of course it will just fall in one direction. So you don't have this coupling. And that's exactly what we see here. If the speed of the wheel is 0, then the coupling disappears, and then you have these two independent horizontal systems. But then if the wheel has some angular velocity, then this coupling appears, and you have the two horizontal directions coupled. And what you can then do is you can reason about how well is the system able to reject disturbances, so external effects acting on the system. What is this graph showing you? Okay, so this is a relatively complicated graph, so let me walk through it very slowly. So we're interested in what size vehicle, how quickly should I rotate the wheel, and what is the effect of the disturbances there. As before, on the y-axis, we're showing the sensitivity to the disturbances. So bigger means that a disturbance has a bigger effect on the system. Here, the three different lines are three different sizes of vehicles. So we're looking at sort of a nominal vehicle, again, about 1 kilogram in mass, and then a vehicle that's half as big and a vehicle that's twice as big, right? And remember, the vehicle that's twice as big will have a mass that's about 8 times as high, right? The same system that we had yesterday. On the graphs, though, the x-axis now is the speed with which the wheel is rotating. So that's how much momentum is in the wheel. And we notice that the top graph shows us the sensitivity to the disturbance torque. So if we increase the speed of the wheel, the sensitivity to these disturbance torques goes down, right? So as you put more momentum in the wheel, we're better able to reject these disturbances. And that kind of makes sense, right? So the faster you spin the basketball, the easier it is to balance the basketball on your finger. There's sort of an interesting aspect, which is the faster you spin the wheel, the less easy it is for you, beyond a certain speed, to reject force disturbances. So there's this interesting trade-off here between the sensitivity to torques and the sensitivity to forces. But this is basically the same tools we used yesterday. So we can now compare different designs in a very straightforward, very principled way to understand how robust they would be to different disturbances. Probably not so important. Let's just go to the video, skipping over the details about exactly how we designed the controllers, because I think it's not that interesting, but we use relatively standard techniques from there on to actually design the control law that computes the desired forces as a function of the sensor outputs, right? And we use the same tools that we used to generate those graphs. So what you'll see in this video is a nominal quadcopter. So that's a quadcopter about 1 kilogram in mass. That's going to be perturbed by a torque impulse, and this torque impulse will be a mass that strikes a protrusion. So this is a quadcopter where we added sort of a stick sticking out from one of the arms, and then we drop a mass on the stick, and that creates sort of a very repeatable impulse that allows us to compare different vehicles. Right, so we notice you have this mass dropping down, it strikes the vehicle, causing the vehicle to fail. What we can now do is, sorry, just to be clear, so you see here there is something underneath the vehicle, that's the momentum wheel, but it's not rotating. So this is just a standard quadcopter. And what you should pay attention to is the torque happens in one direction, and then the motion is just along that direction. So it's a very straightforward, predictable reaction causing this to fail. And what we can now do is we can compare the system that we just saw without the wheel spinning to a system where we have this added angular momentum, we have this additional robustness. So these will be exactly the same disturbances, so exactly the same amount of energy in this impact acting on the system, so the same disturbance torque impulse. But we notice this sort of oscillation, this coupling of the two directions, and the system is much more robust, so it's much better able to reject these disturbances. So we can then reason about this robustness, we can make these predictions using our theory, and then we can validate this in experiment to actually show that you get these improvements that you expect, and you end up with a more robust vehicle. And just to show you sort of the scaling, so this is a much smaller vehicle doing sort of the same thing, where you have the wheel off, you have a big effect of the disturbance, you have the wheel on, we notice that the disturbance has much less effect, right? So if you wanted to design small vehicles, this suggests that it might be worth it to actually put this additional mass on angular momentum to reject these disturbances. And the key takeaway message here is that we don't just go out and build these vehicles, but rather using these tools, we can predict the effects, we can compare these designs, we can reason about the trade-offs before we actually go out and do any experiments, right? And the experiments here ideally are really boring in the sense that they just show us what we already knew. And then last, pretty quickly, I want to just sort of show some recent work where we sort of tried to think way out of the box. This is not so much related to safety so much as I think just sort of an interesting example of mechanical design to hopefully get you guys more excited about mechanical design. So we all know that in nature you have very impressive flight in birds. So here we have an example of a goshawk that can operate through very narrow environments by changing its shape. Just another example of this here with this goshawk flying through this very narrow gap by changing its body shape. And this is very different from what we can do in aerial systems. Typically we have very rigid systems because they're easy for us to analyze. So it's very easy to come up with models for them. So we wanted to copy this using designs. So the idea was to create an aerial system that can do sort of the same thing. So that can in flight change its shape to pass through narrow constrictions and then return to normal flight. We want to retain the good components or the good parts, the good effects that we have with conventional aerial robots, specifically sort of the high reliability, low mechanical complexity, etc. Again, we do this in a very model-based fashion. So we try to model the system and skipping over exactly what's going on here. We try to understand what the different physical components are, what are their relationships, and then look at sort of the design degrees of freedom that we have. So in something like this, there are quite a few additional degrees of freedom to what we would have in a standard quadcopter. Specifically, what we want is we want to hinge the arm that has the propeller to the central body, and then we have a spring that's able to retract this arm. So the idea is when the propeller is producing thrust, it pulls the arm out to operate like a normal quadcopter. When you turn this thrust off, there is a spring that pulls the arm back down. And then you can sort of play with where you put these different components and what their effects are to get different designs and different capabilities in the design. And then how this actually ended up working is you have a mechanical hinge, so you have a rotational degree. Then you have these springs with all of these components being sort of control theoretically motivated. So where do we put them and what stiffness, etc. And then you get something that can do something like this. So here you see the vehicle operating much like this bird, so able to change its shape in real time, change from a normal quadcopter to this constricted shape, and pass through a gap that is narrower than the vehicle could possibly fit through unless it did this morphing. And then there are some sort of controls details, which I think I'll probably skip over since they're not necessarily that interesting. But you then have to reason, of course, about what exactly does this mean and how do I control the vehicle to make sure that it only folds, it only changes shape when I actually want it to change shape, and how do I deal with these additional constraints, etc. Here are a bunch of references if you're interested. As usual, everything I've showed, the research, lots of people contributed to it. You'll find a list of all the people in the lab here. You can see sort of group picture here with UC Berkeley in the background, with funding provided primarily by the agencies we see here. And then just to wrap up, for me, when I think about these cyber physical systems, what I think about is how do I design these complex moving dynamic systems that operate in complex environments at sort of a low level, right? So how do I manipulate the dynamics? How do I manipulate the controller to make the system robust to disturbances, to make the system survive these external effects as well as possible? When I talk about safety, typically we talk about these relatively low-level performance goals. We tend to not talk in these absolutes because it tends to be very difficult to make promises about the physical world because we don't know what the disturbances are, but we can make these sort of statistical arguments that the likelihood of something is negligible. And then I guess the key takeaway for me is that if you tightly couple the intelligence with the physical design, the intelligence can be relatively stupid and still achieve complicated things, right? So rather than taking a Frankenstein design and then writing a Frankenstein controller for it, if you are able to modify the design, you can make your life much easier to do this. So happy to take questions now. If you have other questions, feel free to send me an email. And Martin, I'm not sure, will these slides be made available?
Yeah.
Okay, excellent. And then I guess you'll have access to the slides as well. I'll mail them to you. Excellent. So we have some time for questions, and I'm happy to take any questions. Thank you. Yes.
So your one that had a protrusion, the artificially added one that survived getting hit.
Yes.
Have you trialled it getting hit on the actual body of the drones?
So the difficulty is to make sure you don't hit the propellers. So the propellers are fragile. So let me just.
So I was just thinking the example you used there, the hailstorm.
Right. So if we think about this, so the challenge is to have it be repeatable for these experiments. So the problem is if you think about something impacting the rotors, that need not necessarily be catastrophic so much as it's likely hard to predict the exact effect that it'll have. So the issue there is there will be a lot of randomness in the experiments just introduced by where the propeller is relative to the thing that's impacting you. Clearly, if I'm operating in an environment where the disturbances are such that they will just destroy the propellers, right? And a hailstorm might be of that nature if I have relatively brittle actuators. It's kind of irrelevant how big the angular velocity is as a result of the torque so much as what happens once my actuator stops working, right? Which is a different question than the one we were trying to answer here. But very good question. Lars, maybe you, and then.
Just as a follow-up to that, maybe like suppose you combine these two concepts you present. So this concept was produced from that. What's your experience? What do you think? Would it be better or worse at dealing with such a situation than without the flight? Mark, maybe you could repeat the question.
Sorry, yes, I should be repeating the questions. So the question is, if we combine the ideas of being able to fly with the failure of an actuator with this idea of having an additional actuator, would it be better or detrimental to have the flywheel after the actuator failure? I'm not sure what the answer to that is. I suspect it would not matter too much. And that once you have the failure and you start to rotate the vehicle, you'd want to turn off the flywheel. Because well, I'm not sure. Actually, maybe take that with some salt. But the concept in the background is similar for both. So when you have this rotation, if you have angular momentum, you can exploit the existence of this angular momentum to modify the dynamics to give you different ways that your inputs, your actuation affects the dynamics. And having the flywheel gives you some more degrees of freedom in the controller. So you can imagine that, let's say I have this vehicle and one of my actuators fails. There might be an ideal speed at which to rotate the flywheel after the actuator has failed to make the controller as easy as possible. And I don't actually know what the answer to that is, but it would be kind of interesting because you have the transition from I was flying normally, I have an actuator failing, to eventually I'm flying in this relaxed hover mode. And having the flywheel means that you can probably modulate the speed of the flywheel to make that transition better. So it'll be sort of an interesting challenge to think at, but we have not thought about that at all. Martin, did you have a question?
Yeah. So in your nice design with the bird-inspired morphing creature, you're actually having a hybrid system, and you're partly applying open loop.
Yes.
So how did you deal with that?
So yeah, exactly. So here it's actually a good point. So Walid was talking about these hybrid systems as well yesterday. So this vehicle transitions from the one configuration where we're using the inputs like a normal quadcopter to effectively a brick that's falling back to the normal vehicle. And one way to reason about this in our model is to have this hybrid model where you have the normal quadcopter and then discretely switching to the brick and then discretely switching back to the normal quadcopter. So the way we deal with it is pretty naive. We plan the trajectory in 3 phases. So there's sort of a wind-up where we put the vehicle in such a configuration that were it to fall like a brick, it would fall through the hole, which we then do. And then after that, you recover by deploying the arms and then flying again. So at the moment, this is relatively brute force, naive planning. You can imagine, though, if I manipulate the dynamics as I am folding, so rather than thinking about these 2 absolutes, but think about sort of the gray area in the middle.
Transition.
Exactly. You can do interesting things where you can deploy maybe half the arms initially and use this to do something. But we have not done that yet. Yes?
How is it with collaboration between drones? I mean, like in the video we saw with the 8 drones, and they are automated. I think they somehow may have to neglect where they're flying, or if we think about, I don't know, hundreds of drones that are flying outside, they at some point probably have to neglect their trajectories.
Yeah, so when I have multiple drones, how do I reason about this? How does this affect it? So in this example here, there are multiple drones, but honestly, they are flying independently of one another. So we plan these sort of choreographies, and I'm using we in a very generous sense to myself, because I was not involved in that. But these trajectories are planned naively, just neglecting the fact that these vehicles might interact, but then designed in such a way that if there is a fault, each vehicle is capable of removing itself from the others safely. So for relatively small numbers of vehicles, that scales easily, and I think that would be the correct approach. But if you imagine having 100, 1,000 drones, then suddenly it becomes a relevant question: is it better to have this centralized approach, or rather something which is decentralized, where each agent reasons about itself and its neighbors? That tends to be something that's very popular in the research. The engineer in me is skeptical of the sort of the swarm-like behavior, just because it is so hard to reason about what happens, right? What happens? How do failures propagate through the system? How do I reason about safety for such a system? What happens when you have sensor failures, etc.? But yeah, at a certain scale, the centralized approach typically fails, right? Because the planning will scale as the number of agents cubed or something. So there's a huge difference between going from 10 to 12 and going from 20 to 22, for example. And at some point, it just will break down. I don't know how much time we have. I think there was a question back there.
A few more minutes.
I think there was a question. Yes, Ken?
Very quick one. I'm a computer scientist, so I tend to think about modes and things like in big discrete chunks. Whereas you going through that thing, you've got some kind of PID or thing here, and some different PID in the middle. What's a transition like what does a computer scientist have to think about in terms of
I mean, it's here.
switching out low-level controls?
It's a pretty naive if-then-else statement. So so we have one controller that tracks this trajectory. So the way this works, what we do is we generate an open loop trajectory. So a nominal set of inputs that in an ideal world, if everything were perfect and you applied these inputs, you would start from this initial condition, and a certain time later, you would end at that condition. We track this then by adding a feedback controller that measures the difference between where we are and this desired trajectory, and that keeps us close to that trajectory. And then at this time t1, we are, if we've been doing our job well, we're very close to the desired state that we want it to be. We just turn everything off for a certain amount of time, and we hope that we've made it safely through the gap, and then we turn it back on, and we follow a very similar strategy for the braking. It is violent, so there is a lot happening. It's an extremely dynamic thing, but it's not a problem, right? And of course, there would be a strong discontinuity. So if you looked at the control inputs for this first phase, they'll be relatively smooth. Then there'll be a huge discontinuity here. They'll go to 0, of course. And then at this point, there'll be a violent set of inputs in a sense, because your state error will suddenly be quite large. But then it will hopefully, again, if you do your job well, will decay smoothly to sort of the hover or whatever the next state is that you're trying to achieve.
Do you ever do like model predictive control or anti-disturbance rejection or anything like that?
Yeah, so model predictive control, we do use. So model predictive control, so the question was, do we do model predictive control and similar methods? Yes, it's a very powerful tool, especially when you deal with things that are input constrained, so where you have bounded inputs, which of course you always do. The cost is sort of slightly more complexity, more computation, etc. But honestly, in today's age, there's little reason to not do it unless you're very constrained. The thing I would say, though, maybe is for us, it's very important to understand the simple controller as well, and then base the more complicated one off of it, right? So that we can reason about the linearized, whatever the simplest thing is, where we can actually make these strong predictions on. Because with the model predictive control, where you have just some black box optimizer, it's very hard to reason about as a designer.
Another question. This flywheel, will it have any significant importance if it's flying outdoor and with very quickly changing winds?
So yeah, so the question is, does the flywheel help you outdoors where you have rapidly changing winds and wind gusts, perhaps? Yes, that's sort of the design. That was sort of the picture we had in mind. It should give you this additional stability. I should note, though, and I probably did not make that point loudly enough, it gives you this ability to reject disturbances better, but it does come at a cost because you have to add this additional mass, right? So every gram of weight that you put into this flywheel is a gram of payload less that you can carry, or is a gram of battery less. So if you're flying outdoors, this should give you a more stable platform. So if you're, for example, putting a camera on and you really care about pointing your camera or your sensor, this should help with that, but it does cost you that additional mass. So it is just a heavier system, and of course it also means if this is going to fall on someone's head, right, it's going to hurt more because it is heavier, right? So it does have a cost attached to it, but it should. The wind is exactly sort of the motivating goal. But it's hard to have repeatable wind disturbances, which is why we use this impact as a validation.
Yeah, sure. The last question, then we go for coffee.
Okay.
Questions.
The other one, the one that closes itself, was it difficult to control it in a normal mode to make it not to close itself?
So there is.
I guess you cannot have, you have a value lower than which it closes.
Exactly. So when you look at this graph, what it means is there's. So the question is it hard to control when it's unfolded? There's an additional constraint that you have to respect, which is that if your force drops below some particular value, then the spring, as it's supposed to, pulls the arm in. So you have this additional constraint, and what that does mean is that you do reduce the amount, sort of the space that you can fly in as a normal quadcopter. So you do pay a slight price. It's not particularly hard for us to handle because you already have a minimum thrust, which might be 0, but there is some minimum thrust, and you're just pushing that up. So conceptually, it's pretty easy to deal with, but it does reduce the envelope of acceptable controls.
So
Good.
we should give a big round of applause.
We'll chat in the break. Thank you very much.